Hello friends and welcome to Shri Tech Education YouTube video channel. In last lecture we have studied how to find the natural frequency of free damped vibration. Before that we have seen what is damping, types of damping as well. In today's lecture we will study some terms related to free damped vibration such as damping factor, logarithmic decrement and some problems based on this free damped vibration. So let us start. In last lecture we have seen what is damping. Damping is the resistance to the vibration, or it is dissipation of energy. Now to study what is damping, what are different types of damping in detail, see the link provided in the description, or at the right corner you will get the suggestion link for that video. Click on that link and watch the video completely. Now the types of damping are 4 types we have seen, 5 types we have seen: viscous damping, Coulomb's damping, solid or structural damping, interfacial damping and magnetic damping. So we have seen all these 5 types in detail, and we have seen how to find the natural frequency of free damped vibrations in case of viscous damping. So we have got the formula for that natural frequency of damped vibration as Fd is equal to 1 upon twice pi square root omega n square minus a square, where omega n is equal to square root s by m and a is equal to c by twice m, and cc is a critical damping coefficient. It is equal to twice m into omega n. All these formulas we have got while deriving the formula for natural frequency of free damped vibration in previous video. So you can watch the video in the suggestion link. So we will study next we will see what is damping factor or damping ratio. The ratio of actual damping coefficient to the critical damping coefficient is known as a damping factor or damping ratio. It may be given mathematically as damping factor is equal to C divided by Cc, where C is actual damping coefficient of that damper and Cc is the critical damping coefficient of the damper. Now value of C is generally standard for that your damper, and Cc is the critical damping coefficient required for the system to be critically damped, and that can be given as Cc is equal to twice m into omega, where m is mass attached to that damper and omega n is the natural circular frequency, which can be given as omega n is equal to square root s by m or k by m. Now the damping factor is a measure of relative amount of damping in existing system with the necessary for the critical damped system. Damping factor is a measure of relative amount of damping in the existing system with that of necessary for the critically damped system. That is the significance of damping factor. So remember this formula. We have to solve some problems based on this also. Damping factor is equal to C divided by Cc. Next term is logarithmic decrement. In previous lecture we have seen, while finding the natural frequency of damped vibration, there are the 3 cases, that is over damping, critical damping and under damping. In case of under damping, we have seen this kind of graph of displacement versus time, or oscillation of that mass with respect to time. This kind of fluctuating graph about mean position we have seen, and we have to study one curve, that is exponentially decreasing curve, that is called as a logarithmic decrement in detail. Now what is logarithmic decrement? It is defined as the natural logarithm of the amplitude reduction factor. Natural logarithm of the amplitude reduction factor. The amplitude reduction factor is the ratio of any 2 successive amplitudes on the same side of the mean position. Now logarithmic decrement is defined as the natural logarithm of amplitude reduction factor where amplitude reduction factor is the ratio of two successive amplitudes on the same side of the mean position. Now you can observe in that diagram x1 and x2 and x3 are the amplitudes on the one side of that diagram, and the ratio of this successive amplitude, that is x1 upon x2 or x2 upon x3, is called as amplitude reduction factor, and the natural log of this amplitude reduction factor is called as a logarithmic decrement. Now if x1 and x2 are successive values of amplitude on the same side, then amplitude reduction factor will be x1 upon x2. It is equal to, I can write e raised to 80 into e raised to 80 as a constant. This ratio is constant, just remember that x1 upon x2 or x2 upon x3 is equal to constant. Now as per definition of logarithmic decrement, delta, we will represent logarithmic decrement by delta. It is equal to log, natural log, I may say log to the base e, or you can say as a ln also, natural log of amplitude reduction ratio, that is x1 upon x2, which can be given is equal to log to the base e into e raised to 80, where a is a constant and time period t can be given as 2 pi upon omega d, and omega d, you are knowing that it is equal to square root of omega n square minus a square. We have studied this in last lecture also. What is omega d? It is a circular natural frequency of damped vibration. Omega d is equal to square root omega n square minus a square. Now putting the value of a, constant a, as is equal to c by twice m, and omega n value, sorry, a value as c by twice m, and doing some calculation, we will get delta is equal to twice pi into c divided by square root cc square minus c square. Pause the video and do the calculation on your own. You will get the value of delta is equal to twice pi c upon square root cc square minus c square. So this is the value of delta, that is logarithmic decrement. You have to remember these two formulas for logarithmic decrement. Delta is equal to log to the base e of x1 upon x2 is equal to twice pi c upon square root cc square minus c square, where x1 upon x2 is the amplitude reduction ratio, c is the damping coefficient, and cc is the critical damping coefficient. Now in general, the amplitude reduction factor we can write as x1 upon x2 is equal to x2 upon x3 is equal to x3 upon x4 is equal to xn upon xn plus 1. Remember, these ratios are constant. Therefore, delta formula you have to remember as log to the base e into xn upon xn plus 1. And it is equal to, also we can find it as a twice pi c upon square root cc square minus c square. Remember for the problem purpose. Next, we will solve some problems based on whatever up till now we have seen. We have seen the formulas such as formula for this circular frequency damped vibration fd is equal to 1 upon twice pi square root omega n square minus a square, where a is equal to c by twice m, omega n is equal to square root s by m, cc is the critical damping coefficient, it is equal to twice m into omega n, and we have seen formula for damping factor is equal to c upon cc. We have seen what is logarithmic decrement. Delta is equal to natural log of xn upon xn plus 1, or delta is equal to twice pi c upon square root cc square minus c square. We'll solve problem based on these. These problems are very much important for the GATE also, or some competitive exams as well. So listen carefully. First example, I will read. A vibrating system consists of a mass of 200 kg, a spring of stiffness 80 Newton per mm, and damper with a damping coefficient 800 Newton per meter per second. Determine the frequency of vibration of the system. Now in this problem, one spring, mass and damper system is given, and we are asked to find out the vibration frequency. So we know the formula for frequency of vibration of the system. For damped vibration, Fd is equal to omega d upon twice pi, or it can be said as 1 upon twice pi square root omega n square minus a square. Omega d is circular frequency of damped vibration. First we need to find out that. Omega d is equal to square root omega n square minus a square, where omega n is equal to square root s by m. First find out this omega n, where s is again a stiffness of the spring, which is 80 Newton per mm. Convert it into Newton per meter, and m is the mass of the mass attached to spring and damper. You will get omega n, and you will get the value of a, constant a, by a is equal to c by twice m, where c is a damping coefficient. It is given in Newton per meter per second. Now once you find omega d, put the value in the formula of Fd, you will get the frequency as 3.17 Hz. Pause the video, do the calculation on your own. The simple problem it is. Now next, second problem we will see. The following data is given for a vibrating system with a viscous damping. So it is a damped vibration system. Mass is equal to 2.5 kg, spring constant, that is K, or you can say S, is equal to 3 Newton per mm, and amplitude decreases to 0.25 of the initial value after 5 consecutive cycles. That means after 5 consecutive cycles, amplitude will become x6. Therefore x6 is equal to, it decreases to 0.25 of the initial value. If I consider initial value as x1, then x6 is equal to 0.25 times of x1. This condition is given in this sentence. Determine the damping coefficient of the damper in the system. So here you have to determine the damping coefficient C of the damper in the system. So if you want to find out the value of C, that is damping coefficient, the damping coefficient is in the formula of A, constant A. We know A is equal to, say at the bottom of this slide, A is equal to C by twice M. So there value of C is there. To find out this value of C, we have to know constant A and mass M. We are knowing mass M, but we don't know value of this constant A. First we need to determine this value of constant A. This value we can find from the logarithmic decrement formula. Now we are knowing the formula of logarithmic decrement as logarithmic decrement is equal to log to the base e of x1 upon x2 is equal to twice pi a upon square root omega n square minus a square. Now previously we have studied the formula for the delta is equal to twice pi c upon cc square minus a square. If I expand this formula somewhat, or put the value of c in terms of constant a, I will get this formula as a into twice pi, that is twice pi a divided by omega n square minus a square. So in this formula constant a is there. You can put the value of x1 upon x2 and omega n. You will get the value of a. So we should know the value of x1 upon x2 first. That value you can find out by that relation given in this problem as x6 is equal to 0.25 into x1. So here we are knowing that x1 upon x2 is equal to x2 upon x3 is equal to x4 upon x5 is equal to x5 upon x6. These all values are constant. Therefore x1 upon x6 value can be given as x1 upon x2 into x2 upon x3 into x3 upon x4 into x4 upon x5 into x5 upon x6, that is The x2 value, x3 value, x4 value and x5 value will cancel, and remaining will be x1 upon x6 only. Therefore x1 upon x6 I can write is equal to x1 upon x2 bracket raised to 5. Here we are knowing one ratio, that is x1 upon x6 is equal to 1 upon 0.25, 1 upon 0.25, that is 1 upon 0.25 means 4 raised to 1 upon 5. I will get the value of x1 upon x2. Once I have got the value of x1 upon x2, put the value in the formula of delta, that is logarithmic decrement, is equal to log to the base e of x1 upon x2 is equal to twice pi a upon square root of omega n square minus a square. Find the value of a, and then you can put the value of a in the formula of c. C is equal to a into twice m. Find the value of c. Pause the video and check the calculation once again. You will get the answer of a is equal to 7.65 Newton per meter per second. So next problem. An instrument vibrates with the frequency of 1 Hz when there is no damping. Yes, in this sentence, when there is no damping, the vibration frequency is 1 Hz. And when there is damping is provided, the frequency of damped vibration was observed to be 0.9 Hz. Find the damping factor and logarithmic decrement. These two terms you have to find out in this problem: damping factor and logarithmic decrement. Now, first condition is given in this problem is the natural frequency without damper is 1 Hz. We know that the natural circular frequency of undamped vibration, that is omega n, is equal to twice pi into fn, where fn is equal to 1 upon twice pi into omega n. Omega n, therefore we will get twice pi into fn, therefore we will get value of omega n as 6.28 radian per second. Circular frequency of damped vibration omega d is equal to twice pi into fd, because formula of fd is equal to omega d upon twice pi is equal to, we will get omega d as 5.66. Now we are knowing that one formula of omega d is equal to square root omega n square minus a square. So here we are knowing omega n as well as omega d. We only unknown is a square. Therefore find out first a square from this. So once a square is known, that is value of a is known, we are having formula of constant a is equal to c by twice m. C by twice m. Therefore c we will get as a into twice m. We will get value of constant c, that is damping coefficient, as 5.58 into m. In terms of mass we have got this, because mass is unknown here. We are also knowing the formula of Cc, that is critical damping coefficient, is equal to twice m into omega n, where omega n is also known but just unknown is m. M remain as it is, therefore Cc is equal to 12.56 m. Then put the C value and Cc value in the formula of damping factor. Damping factor is equal to C by Cc. Put the value of C in terms of m, put the value of Cc also in terms of m. Cancel the m value, that is mass value, you will get the value of damping factor as 0.436. Remember, this damping factor value generally comes less than 1. This is the damping factor. Now next is asked logarithmic decrement. We are knowing formula for logarithmic decrement: delta is equal to twice pi c upon square root cc square minus c square. You are knowing the value of c as well as cc in terms of m, that is mass. Put the values, mass term will get cancelled, and remaining answer for logarithmic decrement delta is equal to 3.04 you will get. This delta value is a constant, it doesn't have any unit. logarithmic decrement. Last problem now, fourth problem. The measurement on the mechanical vibrating system shows that it has a mass of 8 kg and that the spring can be combined to give the equivalent spring stiffness of 5.4 Newton per mm. Mass and spring stiffness is given in this sentence. If the vibrating system have a dashpot attached which exerts a force of 40 Newton. Now that vibrating system has a dashpot, that is a damper, which exerts a force of 40 Newton when the mass has a velocity of 1 meter per second. Now remember that the damping coefficient, the damping force F is equal to that damping coefficient into velocity is there. So what will be damping coefficient C? C is equal to F divided by velocity, force divided by velocity. Therefore, in this sentence, indirectly what is given? Indirectly you have been given with damping coefficient C. Force is given, velocity is given. What is force is equal to damping coefficient into velocity. Therefore, damping coefficient C is equal to 40 divided by velocity 1 meter per second. Therefore, C you are given 40 Newton per meter per second. Find the critical damping coefficient. First value is asked. What is the formula of critical damping coefficient? Cc is equal to twice m into omega n, where omega n is equal to square root s by m. Put the value of s, that is stiffness, in Newton per meter. You will get the Cc value as 416 Newton per meter per second. This is the first critical damping coefficient. Secondly, you have been asked damping factor. Damping factor formula is equal to C by Cc. Therefore, value of C is given. What is Cc? Critical damping coefficient. Just you are now found. Take the ratio, you will get 0.096. Third thing asked in this problem is logarithmic decrement. Now formula for logarithmic decrement, you are knowing that delta is equal to twice pi c upon square root cc square minus c square. You are knowing the value of c, you are knowing value of cc. Put the values and find out delta. You will get it as a 0.6. Next, fourth thing asked in this problem is ratio of two consecutive amplitudes. Ratio of two consecutive amplitudes, that is xn upon xn plus 1. In generally, we can say xn upon xn plus 1. Now we are knowing logarithmic decrement delta can be given as by two formulas. One formula we have used in third case, that is 2 pi c upon cc square minus c square. Logarithmic decrement delta can also be given as delta is equal to log to the base e of amplitude reduction ratio, that is xn upon xn plus 1. Therefore, xn upon xn plus 1 is equal to e raised to delta. Now put the value of e and delta. E as 2.7 and delta as 0.6, that is logarithmic decrement. Or on the calci directly you can do the calculation. E raised to 0.6 you will get it as a 1.82, that is the value of xn upon xn plus 1, that is 1.82. The ratio of two consecutive amplitude you will get as a 1.82. Now thanks for watching these videos. Solve the problems by pausing the video. Pause the video, do the calculation on your own. These are simple problems frequently asked in various exams. Thanks for watching videos. Subscribe my channel. In next video we will study the forced damped vibration. Thanks for watching the video.